Hello, I'm Dr. James Wotton of the University of Basel, and I research quantum error correction, and specifically topological quantum error correction. This seeks to keep quantum computers free of errors using particles called anyons. The trouble with anyons is that they don't actually exist in our universe, and they're actually kind of impossible in our universe because our universe has three spatial dimensions and they can only exist in 2D universes. However, we can force them to exist, and in this video I'll be telling you a little bit about how to do that. Normally we would use quantum systems to do this because they have nice quantum properties that we can use, but today I'll be using dice. We can do half the job with dice. Unfortunately it's the easy half, but it's enough to give you an idea of what we're doing. Now here you see a grid that I have drawn with my own fair hand. It has three kinds of square. We have white squares, we have glittery squares, and we have blue squares. We're not going to think too much about the blue squares. We're going to focus on the white and the glitter. So what we do with those is we go around all of the dice, around the square, we add up their numbers and we see if it's a multiple of 6 or not. So for this one we'd look at all of these 4, for this one we'd look at these 2, for example. If it's not a multiple of 6, we see how far it is away from a multiple of 6, and we will do this in two possible ways. For the white squares, we will look at how much higher it is than a multiple of 6, and for the glitter squares, we will look at how much lower it is than a multiple of 6. Okay, at the moment, everything is 6, so they're all multiple of 6s. We've just done that by having everything 6, so 4 6s is obviously 4 times 6 and so on. You don't necessarily need to do it like that. We could do something different. For example, we could put that as a 1 and then we could make this into a 5 and then this could be a 1 again and this could be again a 5. And then now we would look around and we'd see that this is 6 and 6 add 6. And this is, well, we have a 6 here and a 6 there, and so on. So we find that there are many ways of having everything a multiple of 6, but let's go back to the easy one. Now, what we're going to do is we're going to break the rules. We are going to make a square that does not have everything as a multiple of 6. The way we do that is, let's take this red one, and let's make it a 2. Now for every square that doesn't involve that red one, it's still a multiple of 6 obviously, but for this one it's 6 add 2, so it's 2 higher than a multiple of 6. So, oh, slight glitch in the matrix there. That's what happens when you're making impossible particles, even when you're using dice. Now if we add up the numbers around this white square, we find that they are a multiple of 6 plus 2, so let's put a 2 there. If we add them up around here, we find it's a multiple of 6 plus 2 as well. But for a glitter square, we look at how much less it is than a multiple of 6, and of course it's 4 less than 4 times 6, so let's put a 4 there. So now we find that these two squares don't add up to a multiple of 6, and these are the numbers that specify that. Now let's take this and rotate it to a 4. And just to keep track of the ones that we're messing with, let's also replace it with a red dice. Now we'll find that this square is again a multiple of 6. 6 add 6, and these two make 6, so we don't have to have a number there anymore. But this one is 6 add 6 add 6, add 4, so it's 4 higher than a multiple of 6, so the 4 moves there. We have moved that 4. Now if we take this one and replace it with a 2, then this white square is again a multiple of 6, but this one is a multiple, is 2 times 6 minus 4, so this 4 goes there. We've moved it again. So what happened was, when we initially rotated this one, we created a 4 and a 2, and then we found that we can also move these numbers around. So they behave a bit like particles. It's as if we initially had no particles, then we messed with our universe a little bit there, and two particles, a 4 and a 2, sprang into existence, a particle and an antiparticle. and then by poking around with the universe we can move them around. That's one way we can think about it, and it's kind of a nice way, but there's also another way we can think about what's happened here, and that's just that we've got a line of places that we've messed around, and that line of course has endpoints, as lines tend to do, and those endpoints just happen to have numbers. So what's the right interpretation here? Should we think of this as a line with endpoints, or shall we forget about the line and just think of the two numbers as their own particles? Well, in this case, we really do have to think about the line. The line is there, it's well defined, we can't forget about it. These two things are the ends of a line rather than particles themselves. However, let's just note for a while that, let's put these back to 6 for a moment. Hang on a minute. There's a 6 that should be there and disappeared for some reason. I don't know when that disappeared, but it should always have been there. Now, another way that we could have a 2 here and a 4 there is, for example, if we had this one became a 4 and this one became a 2 and this one became a 4 and this one became a 2. So here we have a multiple of 6, here we have a multiple of 6, here we have a multiple of 6, here we have a multiple of 6. It's multiples of 6 everywhere except here and here. So, but now the line, I don't have enough red dice to use the red ones on the ones that I've done, but now the line goes up here, then here, then here, then here, then here. It's a completely different line, but it has the same endpoints. Now what we could do is somehow, because if we didn't use dice, with dice the line is always clear, but if we didn't have dice, we had quantum particles, we could make a quantum superposition of all different possible lines. We could even have it, let me just, oopsie daisy, even bigger glitch in the matrix. Say we had an example where we had a couple of particles, well, a line with a couple of endpoints and another line with a couple of endpoints somewhere. These are the lines that define them, but it could be that we could have the same endpoints but joined up like this. If we somehow got a quantum superposition of it being this and this at the same time, then the lines really aren't well defined anymore, because we can't even tell which particles are at the end of the same line as other particles. So if we can make a quantum superposition of all different possible lines, then the lines don't really make sense anymore, but what makes sense instead is, what still makes sense, sorry, is the endpoints. So the endpoints then really are the only thing that makes sense. They become their own thing, they get their own identity as particles. So a quantum superposition, I should just say, is something where we have many things that are contradictory all happening at the same time because of quantum. Anyway, so how will we do this? Well, actually, it turns out that it's moderately easy. When I say moderately easy, I of course mean really, really hard in real life, but not so bad in maths. All we have to do is look at the blue squares. The blue squares currently, we're not going around and adding up anything, but if we did, and if we defined it in a sort of quantum way, then that would do the job for us. So if we went around adding up numbers, not these numbers on the dice, but some quantum superposition-y numbers in exactly the same way as before, we would get particles that live here as well, and it would turn out that they would, the existence of those particles, having those particles well defined, would force the lines for the particles that live on the white and glittery squares to become a big superposition of all possibilities. So then they truly become particles. That was a bit technical, but just believe me that these numbers become particles. Now, when we did this, we ended up with a 4 and a 2, which add up to 6. And since everything is based on the number 6, you might wonder if that's a coincidence or not. Well, it isn't. Whenever we mess around with the dice, we will always find two numbers that add up to a multiple of 6. Another glitch in the matrix there just goes to show you create universes at your own peril. Now everything's back to a 6. Let me show you something else we could do. We could take this and rotate it, for example, to a 5. And then this square would be 5 more than the multiple of 6. This one would be 1 less. So we have a 1 and a 5. 5 is the antiparticle of 1. 1 is the antiparticle of 5. So this is another pair of particles we could get. We could also have 3 and a 3, or a 1. No, well, you know how maths works. Now let's take this one and replace it with, say, a 4. Let's do it with a red. Well, 5 add 4 is, of course, 9. 9 is 3 bigger than a multiple of 3, and also 3 less than a multiple of 3. So what we find is that we will get a 3 over here, and here we have 6 add 4, which is 2 less than a multiple of 3. So what we've done by rotating this one is caused that 5 to decay into a 3 and a 2. So that's another thing that can happen. So we can create particles and antiparticle pairs, we can move particles around, we can cause particles to decay, we can do all sorts of things. We have particles living on this little crappy diagram with dice. They would be more real if we had quantum and we could make a superposition of all the different possible strings, so we could no longer say, well, it's just the end of a string of dice what you changed, isn't it? But still, they're pretty particly, and the specific kind of particles they are anyons. Now, I should say that because they're not real particles that you would find in CERN, they are usually called quasi-particles. But because they're just some maths that we do and treat like it's a particle. But if it looks like a duck and quacks like a duck, it's a duck. And that is the thought that I will leave with you at the end of this video. Goodbye.